So actually following the former presentation, what we know, and this is why my questions were going through how to simulate visual acuity. What we know in the clinical practice with the patients, the way we address the visual acuity of the patient is through looking at a chart that have some letters that the patient have to say, have to identify. There is a very almost new approach to measure the performance of the lenses, and this applies to contacts and to intraocular lenses as well, that we want to know the defocus curve. That is, how is the visual acuity as a function of the distance or a function of the defocus. And the way the clinicians make it is inducing lenses, adding lenses in the phoropter for each defocus and remeasuring again the visual acuity. When we go to simulations and to optical bench measurements, we cannot simulate that directly. What we do is to measure the quality of the lens that is usually represented. Here we go. It's usually represented with the MTF that represents the optical quality for a single defocus. And what we can do is to measure the MTF at a single frequencies for all the defocus to know which is the optical performance. Unfortunately, this straightforward measurement is not correlated with the clinical visual acuity. And it doesn't go to the next slide. Here we go. So the next step is actually, and there are a few literature on this, that is measuring the area under the curve between a certain number of frequencies and to perform a correlation between the clinical data and the area under the curve to get the expected visual acuity. So there are two main questions, that is, which is the range of frequencies we should be using and which is the equation that better correlates with the expected visual acuity. So in a first step of this work, what we did is to simulate with Zemax a modified Liu-Brimena Model I with a corneal spherical aberration that mimics the average corneal aberration of the patients using white light and simulated it with a Envista monofocal lens, that is the Bausch and Lomb monofocal, that we know pretty well the clinical data. So, and we matched this, the process of the calculating the area under the curve of the MTF with the data of 445 eyes coming from two different clinical studies. Here are the first, there is a lot of equation, a lot of numbers here, but basically is that what I want to show is first that the results of using area under the curve between 50 and 100 are very similar. Second, that after, besides logarithmic and linear equations that do not fit pretty well, and we can see that the correlation, the R square is not very high. Anyhow, logarithmic is 0.95, that is pretty high. The best correlations, we got it with exponential, logistic, and rational approaches in both 100 and using 0 to 100 cycles per millimeter and 0 to 50 cycles per millimeter. The power law equation did not offer good correlations as well. We can show this as well with using this plot where we see how close are the fitting to in both with both approaches. For simplicity, we decided for the second step of this study to get this equation, this exponential equation with the frequencies from 0 to 100. In a second step, we wanted to know which was the expected performance of a new, it's called monofocal, enhanced monofocal lenses. That are lenses, these are monofocal lenses, but are designed to give a little bit of intermediate vision. But what we wanted to know is not only how much is this intermediate, we are really interested in knowing which is the robustness or the variability of these two designs when we use several different amounts of spherical aberration in the cornea, some corneal astigmatism, some IOL decentration, and some IOL tilt. All these values are in inside the limits of normal eyes. So if there are no pathological eyes included in this, so this we can induce this stress in even a larger amount of patients if we go to pathological corneas or pathological eyes. Surprisingly, what we found is that the impact of astigmatism is very similar in both designs, and decentration and tilt, they are very similar as well. So the differences are very small, but and actually they have very low impact on the performance. So we can say that the lens perform pretty well, no matter if they are which are the tilt, which is surprising, because actually tilt and decentration, where residual astigmatism is measured in the clinical practice, decentration and tilt is not that usual. Nowadays, we have new generation OCTs that can measure which is the actual decentration and tilt of the IOL, and we were expecting having more variability or a higher changing impact in the performance when tilted on decentration, but it resulted to be that with these lenses the impact is very low. What was really surprising is that when we changed the conic constant to induce several amount of spherical aberration on the IOLs, we observed that the area of variability, that is the area between the extremes of the spherical aberration between 0 and 0.55, is higher with the standard monofocal than with the new monofocal or enhanced monofocal here. And we can see as well that there is a shift of around half a diopter when we move from spherical aberration neutral to a corneal aberration, higher aberrated cornea. That happens with both lenses, this shift, which take us to the following takeaways. That is that the Aspire lens, that is the monofocal plus, seems to have greater resilience to variations in corneal spherical aberration compared with the standard monofocal. The impact of tilt and decentration is very small to both lenses, and the impact in astigmatism is very similar to both lenses. And that the spherical aberration should be, or the conic constant should be included to, for example, when we calculate the IOL power of the lens, because it's something that we actually measure in clinical practice, but we are not used to take into account it in the IOL calculation formula. So this point can be very can be nice for further generation of IOL calculation formulas. What can we do for you? Well, Bausch and Lomb offers a very large ophthalmic portfolio across different business units, collaborating in next generation product development, integrating optical modeling and clinical needs is possible, and we can act actually as potential bet to test translational results with our platforms. And what can you do for us? Providing new measurement technologies that can improve the accuracy on how we measure high order aberrations of the cornea, how we measure tilt decentration, the effective lens position, everything related with the physiology of the eye will be really interesting. Refining diagnostic to improve IOL selection and personalization, and we can co-develop data-driven tools to improve the patient satisfaction and the surgical outcomes, and as well the surgeon satisfaction. Happy patient, happy surgeon. That's all from my side.